We're going to look at another concept in counting called permutations, and I'm going to take a minute here. We're going to have an R, B, and G color choice. And so R, B, and G. And we'll say that we have these three balls of different colors in a vase, and we pick one out and we don't replace it. So I could pick the red one out, and that means left inside is the blue and the green. So let's say the next one I pick out is blue, and then end green. But I also could have picked out the red one that left the blue and the green, and instead of picking out the blue second, I pick out the green second. Right, that's a possible order I could pick all three balls out. Or I could pick out the blue, followed by the green, followed by the red, and I could do the blue, followed by the red, followed by the green. And of course I could pick out the green first, followed by the red, followed by the blue, or the green, followed by the blue, followed by the red. And these are all the ways I could pull these three balls out. And if I look at this, there's 1, 2, 3, 4, 5, 6 possible ways. Well, what happened was, when I first go to pick, there are 3 choices. But as soon as I remove one, I'm left with 2 choices. And I remove the last one, there's 1 choice left, or 6. And so this permutations, or an ordered arrangement. So permutation, which is an ordered arrangement of items. No item used more than once. And order matters. So permutations are kind of based off of the fundamental counting principle, where we start with the number of options we have, and as we remove one, the options go down. But the options go down in descending order. And so that's why 3, 2, 1. And this happens so often that we have a symbol for it, which is called factorial. And it's an exclamation point. Your calculator has a factorial key. Let me see if I can get the calculator up here. The calculator always comes up on a little screen on this thing here. My apologies for that. Oh, where'd you go? There it is. And if you see the arrow here, let me clear this. And so 3 factorial on TI-84, I go to... It's different on the different TIs. I apologize. Oh, there's the math button. Math, and over to probability, and down to factorial. And so 3 factorial is 6. Now if I had let's see, what is a set of bingo balls? Let's see. Bingo. Can't remember what the highest number is in bingo balls. 75. 75 bingo balls. So if you pull out every bingo ball one by one, you get too large of a number to put in your calculator. Notice that. We very quickly overflooded the memory of what was possible, even though there were only 75 things. Let's see if it shows up. Your textbook actually has a nice thing that shows up to factorial 20. Oops, go to probability, factorial 20. And we get, let's see, there's the millions, billions, trillions, quadrillions, 2 quintillion, 432 quadrillion, 902 trillion, 8 billion, 176 million, 640,000. So 20 objects, every possible order that you could pull them out in, comes to a very large number. And that's the thing that is the non-intuitive part about choice and probability for people, is how quickly the number of patterns come up, how quickly the number in patterns grows. So factorial will be the symbol we use. And so if I do n factorial, I'm saying I want n times n minus 1 times n minus 2 all the way down to 2 times 1. Now, to make this work, we have to say that 0 factorial is equal to 1. And what I think about for this is, how many ways can I choose nothing? And of course we have one way to choose nothing. Now factorials work nicely when we can actually use them in divisions. And let's look at that here. Your book again has some nice examples of this, but I'll just use 8. So 8 factorial divided by 5 factorial. Well, that's the same as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is the same as 5 times 4 times 3 times 2 times 1. And a neat thing happens, because these all end up in 1, I can cancel out. And I'm left at the top 8 times 7 times 6, or 56 times 6, or 336. And so factorial mathematics has this nice canceling that goes on. And that helps us look at a formula for a particular type of permutations. And so what can happen is we can have a total number of objects that we want to pick from. A total number of objects, n, and we're going to pick from them, or the possible number of permutations, and we're only going to take r out. And the formula we're going to get for that is n factorial divided by n minus r factorial. And so this says that if I have, let's say, again, I'll go to the example in the book, if there are 13 players on a baseball team, so 13 players on a team, and I have to choose a batting order of 9. And so that would be 13, pick 9, or 13 factorial over 13 minus 9 factorial, which is equal to 13 factorial over 4 factorial. Now I know all of the denominator is going to cancel like it did here, and it's going to leave me everything down to 5. So I'm going to have 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. And what I'm going to do here, though, is I'm going to make the calculator do the work for me on this, but I'm going to do it in a nice way. Let me switch over to the calculator here. And so I'm going to have 13, and I'm going to pick, again, I'm going to go back to probability on the calculator, and I'm going to go to NPR. And so I have 13 picked 9. And the calculator gives me, let me get my 259,459,200. Let's see if I can write this number appropriately here. 259,459. And 200, right? Yep. So a baseball team of 13 players has this many possible batting orders. And so, again, that's only 13 players, and I need to put them into 9 orders. Look how many possible permutations we have. And this really sets the idea of why there's a hard time for us to intuitively think that. I look at a baseball team and I wouldn't think that there were this many possibilities. And that's why we usually, when we look at batting orders, we tend to have a rule, you want your strongest hitter to go first, right? There's rules people use that immediately cut this number down. But when we're dealing with randomized things, which probability will, or we're dealing with all possibilities, which statistics do, we deal with these large numbers. Now, there's another way that we can deal with permutations that takes care of actually having duplications. So if we have duplicate items or things that are repeated, the repetition can be taken into account from. And so what we have is we have the total number of ways things can happen. If I have n items, but I have repetitions. And the repetitions depend on how many things are repeated. So a good example of this is like words, like the words Mississippi, M-I-S-S-I-S-S-I-P-P-I. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in Mississippi. So n equals 11. But the I is repeated 1, 2, 3, 4 times. So we'll say that there's 4. The S is repeated 4 times. And the P is repeated twice. And so with the repetitions for Mississippi, the total number of ways I could rearrange all of these letters and get different patterns out of it would be 11 factorial over 4 factorial over 4 factorial over 2 factorial. Which, let's see, 11 factorial and the 4 factorial would give me 11 times 10 times 9 times 8 times 7 times 6 times 5. And then now I'm left with the 4 factorial and the 2 factorial. Well, 2 factorial is 2, so we'll make this into a 3. And then 4 factorial is 4 times 3 times 2 times 1. So the 3 is going to cancel that. 4 times 2 is 8. That goes away. And so I'm left with 11 times 10 times 9 times 7 times 5. Or 34,650. And so if I take the letters of the word Mississippi and I mix them up, and because of the repetitions, right, you know, PIP is the same as PIP, even though those were two different P's in Mississippi. And this one pops up occasionally. I think knowing NPR is more important than this. But those are how many ways we can write things where order matters, with or without repetition, and those are called permutations.